Hi everyone, I'm Shashwat, and I'm going to talk about sharp threshold rates for random codes. This is joint work with Venkatesan Guruswami, Jonathan Mosheiff, Nicolas Resch, and Mary Wootters, and I hope the joke in the subtitle isn't too outdated. First, some quick background about error correcting codes. A is trying to send a message to B over a channel, but because of noise, parts of this message may be corrupted. The way to deal with this is that only a certain subset of things that B can receive are actually valid. So if B receives a message which is invalid, it corrects the error by assuming that A meant to send the closest valid message to what B actually received. Formally, a code C of block length n over an alphabet sigma is just a subset of all length n strings over sigma. The rate R of a code C is just the log of its size divided by its block length, and there's a trade-off between the error tolerance of a code and its rate. For example, if the rate is 1, then every length n string over sigma is a valid code word, so no error tolerance is actually possible. We will think of sigma as f cubed for Q constant, n is going to infinity, and the error will be adversarial. So a random code is a subset of sigma to the n, which is chosen in such a way that every point in sigma to the n is included in C with the appropriate probability so that the expected rate of the code is R. Random objects are often important in combinatorics because they often have ideal properties with high probability. The same is true for error correcting codes. You may have seen that random codes are used in the proof of classical coding theorems, such as Shannon's noisy channel coding theorem. And understanding random codes deeply is just a very basic question in combinatorics and error correcting codes, and they can be easy to analyze. So it's a good starting point for understanding other kinds of codes better. One place where people may have seen random codes before is the list decoding capacity theorem. A code C is PL list decodable if for all x and fq to the n, the ball of radius p around x intersected with the code has size strictly less than L. Pictorially, what this means is you have a code, which is just a bunch of points. If you move a ball of radius p around the space, you can never catch L or more points of the code within the ball. So the list decoding capacity theorem says something really interesting. It says that if you want a code which is list decodable for reasonably small list sizes, so L is kind of small, then the rate of the code has to be less than 1 minus HQ of P. In fact, if the rate is even slightly more, then your list has to necessarily be large. The way you show that there are in fact codes which are list decodable with small list sizes at rates slightly less than 1 minus HQ of P is just by bounding the probability that a random code fails to be list decodable using a union bound. In this way, the property of not being list decodable with small list sizes undergoes a phase transition for random codes. That is, below a certain rate, this probability is close to 0, and even slightly above that rate, it quickly jumps to 1, because in fact, no code above that rate is list decodable with small list sizes. More generally, we might ask, how common are these phase transitions for properties of random codes we might care about, and can we understand them? Let's say for binary random codes, if we fix L equals 3, is there a threshold such that if the rate of a random code is even slightly below that threshold, then it is p comma 3 list decodable with high probability. And if the rate is even slightly above that threshold, then it is not p comma 3 list decodable with high probability. In order to characterize and understand these phase transitions, we need some definitions. We say a code property is monotone increasing if given a code C satisfying P, it holds that every code C prime such that C is a subset of C prime also satisfies P. You can quickly check that not being list decodable is such a property, because if your code is already not list decodable with a small list size, then adding more code words is definitely not going to make it list decodable. For property P, we refer to its threshold rate as the largest rate for which a random code satisfies that property with probability less than or equal to a half. And we say that a property is sharp if the probability that a random code satisfies that property jumps from 0 to 1 over an arbitrarily small transition window as n goes to infinity. We're going to write these definitions out in notation, and feel free to pause the presentation at this point to go over that, but I'm going to skip ahead. So the informal outline of our paper is that we characterize the threshold rate for a large class of properties which are also sharp. The way we do this is by noticing that many natural code properties are satisfied if any one of a certain number of minimal sets of code words are present in the code. For example, a code is not PL list decodable if it contains any L code words which lie in a ball of radius P, because then these L code words are witness to the code's non-list decodability. We group all of these possible minimal sets of code words which specify a property into sets of types. Then a property is satisfied by a random code with high probability if a set of code words with such a type is present in the code with high probability. We later define symmetric properties, which include all kinds of things that coding theorists care about, like list decoding, list recovery, and show that every symmetric property has a sharp threshold for random codes, and we also characterize this threshold. Since we're often going to be talking about tuples of code words appearing in a code altogether, it makes sense to view them as matrices. Here, we have three code words, B1, B2, and B3, and we're going to view them as an n by 3 matrix. The columns of this matrix are code words. Before we state and understand the main theorem, we need another couple of definitions. The first one is that of types. So here's our matrix of three code words B. In B prime, I've interchanged the middle two rows of B, resulting in a new matrix of three different code words. In B double prime, I've interleaved the rows of B with each other, and I have another matrix of three new code words. And the point is, all three of these matrices have the same type. Formally, the type is just the empirical distribution over the rows of the matrix. In all three of these matrices, the row alpha alpha beta occurs with probability half, and the row gamma beta beta occurs with probability half, and no other row appears at all. They all have probability 0. We can say that two matrices are the same type if they are row permutations of each other. Another definition we need is that of histogram types. Now, again, I have our matrix of three code words B. And here, I've not only interchanged the center two rows with each other, but I've also individually permuted their indices. In B double prime, I've interleaved the rows of B with one another, and I've also individually permuted every row with a different column permutation. The point is, in a histogram type, the probability assigned to any row only depends on its histogram. So the rows with two alphas and a beta make up for probability half for this matrix, and the rows with two betas and a gamma make up for probability half in the rows of this matrix. And it doesn't really matter within the row what order the two alphas and the beta or the two betas and a gamma appear. We say that two matrices, B and B prime, are the same histogram type if there is a permutation pi mapping the rows of B onto the rows of B prime. And for all I, row I of B and the row pi I of B prime have the same elements as sets. So here's our main theorem, stated a little informally. Suppose P is a symmetric property, and we haven't defined that yet, but the only thing that you should keep in mind at this point is that this includes a lot of properties that coding theorists care about, like list decoding, list recovery, average radius list decoding, and so on. And this property is defined by the inclusion of a matrix among a set of whose type lies among a set of types T. Then if R star is 1 minus the maximum Curie-Shannon entropy of all the types in T divided by B, then for any epsilon greater than 0, a random code of rate slightly more than R star satisfies this property with probability almost 1, and a random code of rate slightly less than R star satisfies B with probability almost 0. So R star is in fact the threshold rate for these properties, and these properties are all sharp. So let's try to see the proof of this theorem. So we'll first do a very simple lower bound on R star using just the union bound. So suppose C is a random code of rate R over FQ to the n. Given B, which is a matrix of little b code words, the probability that all the columns of B appear in C as code words is just Q to the negative n times B times quantity 1 minus R. This is because every column has to appear in the code independently of each other. Then the probability that C contains a matrix of the same type as B, which we call beta, is just this funny expression by simply using the union bound. And if you look at this carefully, you'll notice that this says if R is less than 1 minus HQ of beta divided by B, then this probability goes to 0. So the code does not contain any matrix with the same type as B with high probability. So if P is a property defined by containing a matrix with type in T, which is a set of types, then R star has to be at least 1 minus the maximum over all types tau in T of HQ of tau divided by B. And the question we'd like to answer is this tight? As in, could this threshold rate R star be any higher than this lower bound that you compute by just using the union bound? And I'm going to say something very imprecisely here, only for people who followed previous work by Mosheiff et al. From Fox 2020, which asked similar questions about properties and their thresholds for random linear codes. And the only thing to notice is that if the property we were talking about was, say, list decodability of random linear codes, then the answer would be no. And in fact, this threshold rate can be higher than what you compute by just using the union bound. However, for completely random codes, we have this really cool result, which says that if you use the second moment method, you can show that for a histogram type tau, a random code of rate R star, which is 1 minus HQ of tau divided by B plus epsilon, must contain a matrix of histogram type tau with probability almost 1. So if P is a property which is defined by a set of histogram types, then the lower bound computed on the threshold rate using the union bound is actually tight for completely random codes. However, histogram types don't define properties like list decodability. So this definition is a little too restrictive for us to get really cool results from the coding theory perspective. So we do a little extra work to get there. So to summarize what we have so far, we know that if P is a property defined by containing a matrix with type in T, then the threshold rate is at least greater than this expression. Also, if T has the additional property that it contains a histogram type tau prime, which attains the maximum entropy amongst all types in T, then in fact, we know that R star is exactly this expression, and we managed to characterize the threshold rate and show that the property is in fact sharp. So that's where we come up with the notion of a symmetric property. I'm not going to say this formally in the talk because it is slightly technical and needs a lot of definitions. So feel free to look at the paper and see what a symmetric property is. But we basically show that for symmetric enough sets of types T, it holds that there is always a histogram type T, tau prime in T, which attains the maximum entropy amongst all the types in T. Properties defined by such sets of types are symmetric properties, and they include list decodability, list recovery, average radius list decodability, and all these things that coding theorists care about. And for all of these properties, R star that we computed from the union bound is in fact the threshold rate, and these properties are sharp in the way that we've defined the word sharp. So our full results are a little more than what we've talked about in this little presentation, but we saw that we are able to characterize the threshold rate for symmetric properties, and these properties included a lot of things we would traditionally care about as coding theorists. We also give analytic estimates for the threshold rate for noisy list recovery, in our paper. The reason that we do this for noisy list recovery is that it contains list decoding and all of these properties as it implies the results for those properties as well. So it's a more general version. We provide an algorithm for efficiently computing the threshold rate for list recovery up to any small additive error. We precisely compute the threshold rate for P,3 list decoding for binary random codes. Remember, this was the motivating question that we asked at the very beginning. Like, could we even answer this very simple question very precisely for random codes? And we can, and we get that the threshold rate is in fact this. This expression immediately may not mean so much, but it is kind of cool because we also did a similar computation for random linear codes. And for P,3 list decoding of binary random linear codes, we get a different threshold than for completely random codes. So it's nice that our methods can get very fine-grained information and even precisely pinpoint such differences between random and random linear codes. And then we also precisely compute the threshold rate for a random code to be a perfect hashing code, which is also a special case of list recovery, but it's still a cool result that people have asked about in previous work. So that's it. I hope you enjoyed this little talk and that you'll have a chance to look at our paper. And thank you for your time.